Hello students, welcome back. We have one more section to go, and that's section 4, additional examples of continuous random variables. We have these examples here, and among those, latter 3 examples are de-emphasized in gray. Now, among the top 3 examples, the third one, chi-square distribution, is relatively important for the latter 1/3 of the course. But then again, this requires some knowledge of gamma function. In fact, chi-square distribution is a special case of a gamma distribution. And that's the topic for the second example here. But then again, gamma function requires exponential function. So that's where we're going to begin. The exponential distribution. And here's the definition. Let lambda be a positive real number, and we define exponential distribution as a continuous probability distribution given by this PDF, probability density function. When x is less than 0, then the density is constantly 0. There's nothing there, so we can consider only the case when x is greater than or equal to 0. When x is greater than or equal to 0, non-negative, then we have this exponential expression. Now, is this a valid probability density function? Well, one way to see it is to check the graph, and indeed, to the right goes down to 0 because lambda is positive, e to the negative lambda x goes to e to the negative infinity, which is 0. So we have nice behavior to the right hand side. So there's a good chance that this has finite area, or more precisely speaking, area has to be 1, the total probability. And to the left, there's nothing because you see when x is less than 0, density is constantly 0, so we don't really have to express this 0 to the left hand side. As for the integral computation, it's an easy computation. It goes like this. Antiderivative is easy to find. And then if you take the derivative, negative lambda comes out as coefficient here by chain rule and collide with this negative. We have just lambda. So everything is good. Now, how about the CDF? When x is less than 0, then density is 0, there's nothing there, so it's no surprise that we have 0 there. Now, what if x is greater than 0? Is this what we really get? Well, one way to check is to take the derivative of this and see if we get this. And that's an easy computation. Derivative of 1 is 0, so that goes out, and then this derivative, yeah, that's fine. But then again, what if you don't know this? In that case, you'll have to find out through an antiderivative computation. You can do it like this. When x is greater than 0, when x is greater than 0, capital F of x is an antiderivative and that's the antiderivative lambda e to the negative lambda x. I don't need color. And then what is this antiderivative? It is negative e to the negative lambda x, isn't it? And then we need integral constant plus c. Okay, all right, we have infinitely many possibilities because I don't know what the c is. How do we find out? Well, please recall that f of positive infinity has to be 1 because everything was accumulated. And what is f of positive infinity is this expression here when x is infinity. So we get this. And what is this? E to the negative infinity, that's 0. So from here we get c equals to 1. And therefore we can replace the c by 1, and that's precisely what we have over here. That's one way to check the cumulative distribution function if we do not know this in advance. If you already know this, then you can take the derivative and check. That's easier. But if you don't already have it, then you can get it through antiderivative computation. But then again, this is not really the best way. Much better way, as a matter of fact, is to use the definite integral instead. So integrate from negative infinity to x, f of t dt, and from negative infinity to 0, there's nothing there. So integral is actually from 0 to x, and then this lambda e to the negative lambda x, this expression, as in the density. And then the rest is just antiderivative computation and the fundamental theorem of calculus. This is 1, so we end up with c equals 1 as before. By the way, here's a visualization. Red is the horizontal asymptote, y equals to 1. Alright, so much for the PDF and CDF. Now, how about the expected value and standard deviation? They require integration by parts. So if you're not completely done with Calculus 2, maybe you want to skip this. Or even if you're not completely done with Calculus 2, and if you want to go ahead with integration by part and check it, you can go ahead. Here we go. That's the integral you want to calculate. And for our purpose, it's going to be a little bit better if you write like this. And then this one is u, and this one is v prime, excuse me. So u is x, v prime is lambda, e to the negative lambda x. Therefore, u prime is 1, v is negative e to the negative lambda x. That's the setting. And integration by part formula, u times v. So u times v, so we get this, and then go from negative 0, 0 to positive infinity. And then we have u prime times v, right there. 1 times something, so 1 does not appear. And then we have negative sign there, but we have negative sign from the part of this integration by part formula, so they collide and become positive. And then just one further antiderivative computation, because this is easy computation of antiderivative through reverse chain rule, and then apply the fundamental theorem. Plug in infinity, plug in 0, subtract one from the other. If you have e to the negative infinity, that becomes so dominant that any x to the whatever power is all killed. You can easily check those through L'Hopital's rule. Exponential stays downstairs, stays the same, and x to the whatever power just goes down to 0 by taking derivative over and over again through L'Hopital's rule. So eventually everything becomes 0, and all the e to the negative infinity part all becomes 0, and then the only thing that survives is e to the 0 power. So in the end, what you get, we have 1 over lambda. That's the expected value. variance is, well, you have to use another integration by part twice. But it goes like this. Variance is expected value of x squared minus expected value squared. And by the way, expected value was 1 over lambda. So you have to calculate 1 over lambda squared in the end and subtract. How to calculate this? It turns out it's just integration by part twice. That's my v. That's my u, excuse me. And this is my v prime, as before. So u v, never mind. Why did I erase that thing? U is x squared this time. V prime is lambda e to the negative x squared. That thing. U prime is 2x. V is so here that's u, and that's v prime, u prime, v, and apply the integration by part formula. U, v. So u times v, including the negative sign, we have that. And then integral of u prime v. Here's u prime. And then v, which comes with negative, but then again collide with a negative sign from the integration by part formula. So this becomes positive. And then please do not forget expected value squared, which was there before. So this part is all okay. Plug in infinity, then e to the negative infinity times something, that's going to be 0. Plug in 0, 0 squared, that's going to be 0 too, so it disappears. And here we have another integration by part. Do that again and do the same thing. Then e to the negative infinity part will all go down to 0. The only thing that's left is e to the 0 power part. So what do you have in the end? 2 over lambda squared minus 1 over lambda squared. So we end up with 1 over lambda squared. So that's my variance. And taking the square root, we get the standard deviation of 1 over lambda. So there goes the exponential distribution. And as for gamma distribution and stuff, let's talk about those in a separate video. Let's stop here for now.